time we talked about potential differences or voltages. We talked about current. And we talked about resistance. And there are fairly specific definitions for both a volt and an amp. The unit of resistance, ohms, is simply defined in terms of the other two values. So 1 ohm is the amount of resistance which will give you a current of 1 amp at a potential difference of 1 volt. And the three terms are related to each other by that little equation, which is called Ohm's law. And you are going to become very, very familiar with Ohm's law. It comes in a variety of forms. This is the most common, E equals I times R. Or you can switch it around a little bit. The current is equal to the voltage divided by the resistance. Or the resistance is the voltage divided by the current. One of those three, any one of those three terms you'll find quite useful working and trying to work out simple circuits. One thing some people use to try to remember is that little emblem. So E equals I times R, or I is E over R, or R is E over I. It just helps you to remember which goes on the top and which goes on the bottom. So, let's try a simple circuit here. Let's see, I've got myself somewhere I had a sheet with some numbers on it. Okay, I've got a 12-volt battery. A 4-ohm resistor. Oh, heck, what the heck, let's put in a switch. Okay, now I haven't gone to all the trouble of drawing the switch. I'm going to turn the switch on. What's the current going to be through there? Okay, what form of Ohm's law are we going to use to get there? See, I is
E over R.
okay, so that's 12 over 3 amps. Okay, let's just switch it around a little bit here. So that works out to, okay, E equals IR 2 times 60 120 volts. I'll give you one more. What were those values again? Oops. Now, pull a little quickie on you. I've given the current in milliamps. Now, do you remember there was a section in one of the appendices talked about the milli, kilo. What is it, how much is 1 milliamp?
Half an amp.
1 milliamp,
Smaller.
1,000, decimal
Yes.
001.
Yeah, okay, so a millivolt is a thousandth of a volt. So 500 milliamps, or same thing with current, of course, a milliamp is 1/1000th of an amp. So 500 milliamps is how much?
Decimal 5 of an amp.
Okay. Now, the catch is here, when you're using Ohm's law, all of your measurements, the voltage, current, and the resistance, must all be in the standard unit. So it must be in volts, amps, or ohms. And if you get a question that has milliamps, you've got to convert that back. To amps. So that's equal to 0.5 amps. When you're dealing with decimal values, you know, I could just say that 0.5 amps. The problem is when you're reading it, you don't know whether that's a mark on the page or whether it's a decimal point. So when you're writing a decimal, always put a 0 in front of it. So that's a 0.5 amps, and then everybody knows that that's a decimal point. Okay, what's the resistance here then?
18.
Okay, 18 ohms. The voltage divided by the current gives you the resistance. How many kilo ohms is that?
0.01.
Okay. All right. Well, let's just mix things up a little bit more here. Okay, I've got two resistors. Would anybody care to guess how you would?
Resistors in series, you add.
Okay, so got current going around through here. The voltage drop across this plus the voltage drop across that is going to be equal to the supply voltage. So the total resistance okay, so if this is 120 volts, forgot to bring my calculator tonight, so I have to make these things. So 50 ohms plus 70 ohms is 120 ohms. So the current would be 1 amp. Okay. Okay, what's going to be the question here now is what's E? The first thing you got to do is take those resistors and combine them together. So one is 25 ohms, this one's 75 ohms. So the equivalent, the total resistance is 100. Just gonna change this a little bit. Current is 100 milliamps. Okay, how much is the voltage? So, E equals I times R. That's R is 100 times, okay, this is 0.1. So we've got 10 volts. Okay, just here's a simpler one. If R1 is 86 ohms and R2 is 2.2 k ohms. Okay, what's the total? Now, I'm kind of playing games with you a little bit here. Mathematically, that's exactly correct. In the real world, a resistance defined to 4 digits is pretty much is not something we normally work with. So you would actually consider that to be 2.3 k ohms, 2.3 kiloohms.
And then convert it to 2,300 for the,
So if you're then doing more calculations, you convert it to 2,300.
okay.
Anybody want to take a wild guess? What would be the color coding on this one? 2.2 k ohms.
Red, orange.
Red, brown.
Oops.
Because it's 3 decimals.
2200.
Oh, kilowatts.
So that's 22 k ohms. So instead of the orange, it would be
You want
I only want 200.
Oh.
So that will be red, red, red.
Red.
86 ohms. What would be the colors for that?
Gray, blue, and black.
Okay, 86, gray, blue, black. Okay, we've just about beaten this piece to death. So I want to do something just a little different. Now, those two resistors are connected, they're not in series, these are parallel. There's a, I'm gonna whip out on you here and not go through the derivation of this. There's the formula for it. Parallel resistance is R1, R2, R1 times R2 divided by R1 plus R2. If you wonder where we got that, grab me over coffee time and I'll go through it with you. Okay, let's got two resistors there. One is 100 ohms, one is 50. Okay, make this one 100, make this one 50. What is the total resistance? What's the total resistance there? Okay, so we've got 100 times 50, that's 5,000 divided by 100 plus 50.
33.3. You want a decimal in that?
Normally we just stick with the,
Okay.
for most resistors, particularly the 20% ones that you're normally working with, we only have two significant digits. So what would be the color that, what would be the color coding on that? Orange, orange, and black for no reasons. Okay, just a quick thing here. When you have series resistors in series, the total resistance is always higher than either of the resistors. When they're in parallel, the total resistance is always lower or less than either of the resistors. So 100, 50, end up with 33 ohms. Okay, here's another pair. Just for, if I have I want to get a total resistance. That's what I want to get, 100 ohms. And the one resistor I've got is 300 ohms. Okay, this is a 100 ohm resistor. Sorry. This is a 300 ohm resistor. And I want the total resistance across here to be 100 ohms. What kind of a resistor would I put in parallel? Let's go back to that same equation, that same. Okay, so 100, which is what we're trying to get, is 300 times the other resistor, divided by 300 plus. So all we have to do is we want to solve for R2, and that's just, this is a little bit more messy than some. So what we're going to do is we're going to get this bit out of the bottom here, multiply both sides of the equation by this. So on one hand we have 100 times 300 plus R2 is equal to so 30,000 plus 100 R2 equals okay. Now I can get these, put those two together.
Sorry, just a second.
Yep.
3,000 is 100 times 300. 30,000, I mean.
Yep. 1, 2, 3, 4 zeros.
Okay, and then where did this next 100 come from?
Okay, so what I did is I multiplied 100
Yes.
times that and 100 times that.
Okay, got it, thank you.
Okay, so 30,000 is equal to, I'll subtract 100 R2 from this side and 100 R2 from that side, so that's equal to 200. Okay, let's get rid of some zeros. And we'll get rid of that 2, make this. So 150. So I start out with a 300 ohm. I put 150 ohms in parallel with it, and the total resistance is 100 ohms. Basically, whatever resistors you've got in your box, you can make almost any resistance you need. Now, the other nice thing about this, when you start combining resistors like this, you get more, you can dissipate more power. If these are all 0.5% or half-watt resistors, by having two of them, you can dissipate a watt instead of just a half-watt. It's also handy if you need to trim, if you've got a resistor that's almost what you want. If it's a little bit too high, you can put another resistor in parallel with it and drop it down a little bit. So if I've got a I've got a 300 watt or 300 ohm resistor, and I only want 250 ohms. Then I put about, I don't know, 600 or 700 watt ohm resistor in parallel with it, and the net is what I want. If you need to raise the resistance a little bit, you put a little resistor in series with it. Gonna make it a little messier yet, but we're not gonna waste a whole lot of time. If I had resistors like that, I've got two in parallel, and then they both feed into another one in series with the pair. How would you solve something like that?
Parallel first.
You want to know your total resistance? Is that
Yeah,
right?
we want to know the total resistance. So Terry is suggesting that this value is the equivalent of these two, and then you've just got a series string to add.
Yeah, she's absolutely right.
The other possibility that you can come across is this sort of thing. So if you combine those two, and then you've got just an ordinary parallel thing.
It's just like Starlight.
Okay. Now you can use, in some situations, you may run into something like this. And I think in the appendix in the book it describes the formula for doing that. It's very similar to what you had for two resistors in parallels, except you got R1, R2, R3 over R1, R2 plus R2, R3 plus R1, R3.
You could solve the first two and then for that.
Or you could, yes, exactly. You can solve these two,
Solve for that, then make another parallel.
and then make another pair with this combination of that. Yep. Works out exactly the same way. We already mentioned, okay, the voltage drop, the total voltage drop around the circuit, is equal to the sum of all of the individual voltage drops across the resistors. Okay, that's the bulk of this chapter with its back broken. One more thing that we want to take a look at. Power. Now, anytime you have a force and you move through a distance, or a charge that you move through a potential difference, you're doing work. Now, the power is the rate at which you do that work. So if I have a potential difference from here to here, and I take a unit of charge and move it up quickly as a high current, more power taken. if I take the voltage difference times the current, that gives me the power. So 12 volts and a current of 10 amps would be 120 volt or 120 watts. So power is measured in watts. Now, if we play around using Ohm's law, what is I? What if I go back to Ohm's law? I equals what?
E over R.
Okay, so I can substitute E over R. So I can also calculate the power of the circuit by taking the square of the voltage divided by the resistance.
Multiplied by the voltage.
So if I substitute for the voltage, E equals IR. So there's three ways of calculating the power in an electric circuit. Volts times amps, volts squared divided by the resistance, or the current squared times the resistance. And those three forms, they're all on page 310. So a 100-watt lamp running at 120 volts would take how much current? So 100 watts would be 120 volts times the current, or 100 over 120, what's that work out to?
0.83. So 833 million.
Okay. Or 0.83 amps. Or 833,000 microamps. Let's see, what else? I've got some more. Oh, if you're looking at page 311 in the book here, there's a possible misprint here. About 3 inches down the page says E equals the root of 235. And then what there should be between that and the 15 volts is almost equal to. There was, now while we're being editors, back in the appendices, let's see if I can find square at the bottom of the page, it says I equals P over R. There should be a square root sign on that.
Where is it? What page is it?
A1,
Appendix 1-4. And there's another one further up the page, the third box down from the top. It says, if A squared equals B, then A equals B. A equals the square root of B. And at the bottom of page, going back into the text, bottom of page 311, there is another form of that triangle that I put on up on the board to start relating volts, amps, and ohms. And this has been, this circle thing is a summary of that entire chapter. So if you've got, for example, if you're trying to calculate watts from the top left corner of it, it's either E times I, or I squared R, or E squared over R. And the unit is in watts. And so on. So those are all your power equations and your Ohm's law equations, all roll up into one nice
wire,
hmm?
wire. The letters in the center spell
Oh.
wire.
Okay, I hadn't seen that before.
That's pretty good.
That's neat. Okay, and then on the following page, it's just a little bit more restating this thing we said earlier. If you try to put more power through a resistor than it is rated for, it will spring a leak and all the smoke will come out of it.
You gotta track with the smoke breaker.
And then at the very bottom of the page says, go through the question bank again. There's lots of these questions. Most of them are not terribly difficult, but you will find a bunch of these on the exam.